Okay, I'm excited. Here we go. Here we've got an alkene, 1-butene, reacting with HBr, hydrobromic acid, in a reversible reaction to give 2-bromobutane as the major product. So by major product, I mean that most of the product will be this. I'm not saying that there's not little bits of some other thing. The more I understand about this reaction, I can apply those insights to other reactions, or maybe biochemical reactions, to better understand just how the world is coming together around me. So we aren't just going to take these things on faith. We want to dig in and understand the mechanism of these reactions, how they work. More language development. So in organic chemistry, language isn't just words. Language is drawing. We have a very specific language of drawing that I want to talk about right now, arrow pushing. Arrow pushing is a powerful technique to communicate organic reaction mechanisms. Okay? It's really, really important that we get this right. A full arrow denotes a pair of electrons moving. So electrons are going from something with excess electrons to something that wants electrons. Steps are separated. So I'm not going to draw 4 molecules all coming together in some like beautiful trick billiard shot configuration. That's not how it works. All right. I'm going to separate this happens and then this happens and then this happens. There's kind of a cause and effect relationship there. And finally, the arrow direction is really important. When I draw an arrow, I am starting where the electrons start and ending where they end up. So I'm starting from where the electrons are rich and I'm going to an electron poor thing. I'm going to be careful to not draw my arrows backwards because that's wrong. I'm pulling electrons away from this carbon. So now this carbon will only have 3 bonds. I'm making a new bond from this carbon to this hydrogen. And I'm having to then break this hydrogen-bromine bond. And so this carbon only has 3 bonds. Its formal charge would be positive, right? It's losing electrons. So this is a full positive charge on this carbon. This carbon has 4 bonds over here, and it has 4 bonds here. So I have a new bond between that carbon and that hydrogen. So this carbon's still neutral. Okay? And then my bromine has a negative charge because I took these electrons and put them on the bromine. So overall, this is neutral, just like this overall is neutral, right? And it better be, because I'm not creating any new charges as I do this. Okay, so new bond here, bond broke here. Okay, so now what? Well, I've got this really positive carbon over here, and I've got this negatively charged bromine over here. So now this is electron poor, and this is electron rich. So these, here comes the arrow, these electrons will attack that carbon. To communicate this verbally, what I would say is that my alkene nucleophile attacks my HBr electrophile. We usually use Marshall language like that, unfortunately, the language of attack. I'm going to then break this HBr bond, end up with Br minus. And because electrons are pulling away from this carbon, it becomes a carbocation temporarily. The bromine then reacts with that carbocation to give me this product, 2-bromobutane. When I add HBr to 1-butene, I mostly get this 2-bromobutane, but I do get some minor products. So for instance, I get a little bit of 1-bromobutane. So that raises the question, why? Why do I see more of this than I do of that? And for that, we need to think about the intermediates that would give us these products. This major product comes from an intermediate that looks like this. So then if we follow that same logic, this product would have to come from an intermediate that looks like that, with a charge on the end of the 4-carbon chain that then bromine would bind. So really, our selectivity question is which of these 2 intermediates is easiest to get to. It turns out that this carbocation is more stable than this carbocation. That's shown here. So this carbocation with the cation on the end of the chain is much less stable, higher potential energy, than this cation where it's not at the end of the chain. And I'll explain why that is in just a second. The barriers to form those are also higher for this one than for that one. And so forming this carbocation is faster. And so the rate of formation of this bromide is going to be much larger than the rate of formation of this bromide. Why is that cation more stable than that cation? It turns out that more substituted carbocations are more stable. So this is more stable than that secondary carbocation, and primary methyl carbocations are very, very unstable, and we will hardly ever see them. Why? Why are more substituted cations more stable? Well, this is kind of a hairy concept, but we can call it hyperconjugation, which is one of my favorite words. Hyperconjugation. Hyperconjugation isn't just the ordinary resonance that we draw with pi orbital to pi orbital. This is something different. In hyperconjugation, we're thinking about filled sigma orbital overlapping some empty orbital, in this case an empty p orbital. So these cations have this empty p orbital here. If I've got some substituent next to it, that means that I've got at least one sigma bond here that can line up with and overlap this pi orbital. When orbitals overlap, they mix. And so since this is overlapping, this empty orbital can overlap this filled orbital. 2 electrons end up going a little bit lower in energy. This is a stabilizing thing. So again, more substituted cations are more stable. That is due to hyperconjugation. And so that explains why this is lower in energy than this is. All of this is summarized as Markovnikov's rule. So Markovnikov was a Russian. You'll see that name transliterated into English lots of different ways, 2 F's at the end. Any way is as good as any other way. Markovnikov did his work more or less at the same time as the periodic table was put together. So I think Markovnikov's rule actually predates the Mendeleev's periodic table by a few years. But they were more or less at the same time. Markovnikov's rule tells us that the major product in this reaction is going to be the more substituted product. So the more substituted bromide is going to be major over the less substituted bromide. And that's because the more substituted product comes from the more stable intermediate. So we would say sometimes we will get the Markovnikov product from this reaction. Other reactions will give us products that we might call anti-Markovnikov. That's not because they're an exception. That's not because this rule only applies sometimes. It's because things that give anti-Markovnikov, less substituted products, are going by an entirely different mechanism that has entirely different intermediates to talk about. Okay? But when we say Markovnikov addition gives us more stable or more substituted products because those come from more stable intermediates. As I said, chemistry is a way to solve problems and to predict the future. So this is how we might write some of these things, maybe on a test, or this is just how chemists communicate. So I would put a reagent or a reactant here. I would usually put the smaller thing maybe over the arrow. Whether it goes over the arrow or under the arrow really isn't that important, so I wouldn't draw too much importance from that. I'll usually put that above the arrow, and below the arrow I'll put less important things like solvent or other directions. But again, don't put too much emphasis on what goes above or below the reaction arrow. So basically this is asking, when I treat this alkene with HCl and I have an excess, which means I have way more HCl than I need, and I have some inert solvent, so I'm not going to worry about solvent reacting. What product will I get? I'm going to think about this thing reacting just like I had the butane before. Again, chemistry is not a sense of memorizing every single molecule that could react. That would be terrible. Chemistry is about learning concepts about how different things react, how different functional groups react. So once you've seen one alkene go and attack some HX, it's all the same, right? Just because this isn't butene doesn't mean it doesn't react the same way. And HCl reacts more or less like HBr. at least as a first guess. And so that's the arrow I'm going to draw. Arrow starting at the pi orbital, going to hydrogen, breaking bonds to chlorine. My intermediate, I've got this cation. It's a tertiary carbocation. It's pretty stable, right? Remember, the more substituted, the more stable. And that's going to react with the chloride up here, the Cl- I just made. And so I'm going to get this Markovnikov product, the more substituted chlorine. I am not going to make the positive charge on the far end. I'm not going to make this primary cation. And so I'm not going to get chloride to add to this end of the double bond. So I'm not going to see these. This is going to be my major and maybe only product.